So let us understand the basics of combustion calculation. The main, the main objectives of combustion calculation are to find the weight or volume of minimum or theoretical air required for combustion of given amount of fuel. Secondly, it is percentage of amount of excess air used per kg of fuel. Percentage of the air used is air supplied or air used is given, and we are supposed to find out the amount of air which is supplied in terms of kilomoles. Third is percentage composition, that is by volume or weight of combustion product, which could be dry or wet depending on the numerical given, formed on burning a given quantity of fuel. Let us consider some important points. The first one is mole concepts. Here, number of moles can be calculated by dividing weight of the substance divided by its molecular weight or molecular mass. If the weight of the substance is in kg, then dividing it by its molecular weight, we get the moles in terms of kilo or kilomoles. If the weight of the substance is given in gram, then we get in terms of gram moles. If the weight of the substance is given in milligram, then dividing it by the molecular weight, you will be getting the moles in terms of millimoles. So number of moles multiplied by molecular weight will be giving weight of the substance in kg if it is kilomoles. Similarly, if kilomoles we multiply it by 22.4, then we get volume of that substance in meter cube at NTP. Next is composition of air. The major constituent of air is considered to be oxygen and nitrogen. If we consider by volume, oxygen is 21% and nitrogen is 79%. Same thing if we consider by weight, then it is 23% of oxygen and 77% of nitrogen. But in our subsequent solving of the numerical, we will be going with by volume. Now let us calculate average molecular weight of air. We know that 100 kilomoles of air will contain 21 kilomoles of oxygen, 78.06 kilomoles of nitrogen and 0.94 kilomoles of argon. So, average molecular weight of air, we consider it as 21 into 32, where 21 is the 21% or 21 kilomoles of oxygen multiplied by the molecular weight of oxygen, which is 32, plus 78.06, this is the kilomoles of nitrogen, multiplied by 28, which is the molecular weight of nitrogen, plus 0.94, that is the percentage of argon in, or the kilomoles of argon in air, multiplied by 39.94, which is the molecular weight of argon. And we divide it by 100 since we are considering 100 kilomoles of air. So we get the molecular or the average molecular weight of air as 28.9522, or in general we consider it as 28.95. Now let us understand some important atomic and molecular weights. Carbon, its atomic weight is 12 and so is its molecular weight. Hydrogen, it is 1, but when we talk about hydrogen molecule, it has got 2 atoms of hydrogen coming together. It is a diatomic molecule, so its molecular weight is 2. Oxygen, atomic weight 16. This is also a diatomic molecule, So its molecular weight is 16 into 2, that is 32. Nitrogen, it is 14 atomic weight. It is also a diatomic molecule, so 14 into 2, its molecular weight is 28. Sulfur, its atomic weight is 32 and so its molecular weight is also 32. So these are few atomic weights and molecular weights which is required to be remembered. Rest other molecular weights can be calculated. As you can see, this is carbon monoxide where we have one carbon and one hydrogen. So for one carbon it is 12 plus, since we have only one one oxygen atom, so it is 16. So 12 plus 16, it is 28. Next is carbon dioxide, one carbon, so here we are having 12 plus 2 oxygen atoms, so it is 2 into 16, that is 44. Sulfur dioxide, it is 32, sulfur 32, 2 oxygen atoms, so 2 into 16, so 2 into 16 is 32 plus 32, this comes out to be 64. This is water, H2O, wherein we have 2 atoms of hydrogen, so it is 2 into 1 plus 1 oxygen plus 16, so this comes out to be 18. Similarly, these are some of the hydrocarbons which you can go through in the similar way and find out its molecular weight. So for solving this combustion calculation, so it is very important that we remember the molecular weights of carbon, hydrogen, oxygen, nitrogen, sulfur, and the molecular weight of air. Only if these molecular weights are known, we can solve this problem easily.